talk Markov generators of low density limit, the locally generic case. So please, you have 25 minutes. Please start.
Thank you. First of all, I would like to thank the organizers for the invitation to this interesting conference and to give a talk. So this is the title of my talk, and it's a talk based on joint work with Cardi, Fañola, Garcia, Guerrero, and some others. My main aim is to describe the class of low density limit Markov generators, the role of the degeneracies in the structure of generators and invariant states for this class of semigroups. And if the time is enough, I will show some examples of invariant states exhibiting the breaking of the similarity principle. The outline of my talk is a brief description of weak coupling limit type Markov generators. So in this part, I will take advantage of the previous talk by Fernando. So I will go rather fast in this part. And after I will give a brief introduction to the low density limit Markov generators with some emphasis in the locally generic condition, the structure or invariant states, and the breaking of the similarity principle. So as Fernando told, both classes of generators, the low density limit and the weak coupling limit, are associated with a reference Hamiltonian that is assumed to be a positive Sevalian operator with discrete spectral decomposition like this one in equation 1. The epsilon m are the eigenvalues and the p epsilon m are the projections, the spectral projections. So in limit time generators, only the positive frequencies, only the positive Bohr frequencies plays a role. As Fernando explained, the generator is a sum of generators, one associated with each Bohr frequency. And this is the structure of the generators for a given Bohr frequency. So the structure of invariant states is described here in this slide. First of all, it is convenient to distinguish this subspace, the WD, that is the intersection of these kernels. The kernels, or these kernels are the kernels of the Krauss operators, the omega, and we can prove that if a state rho commutes with the projection with orthogonal projection on this subspace, then it can be decomposed into two pieces. One of them supported on the WD subspace, and another part supported on the orthogonal. Moreover, if the state is invariant, then it can be written as a convex linear combination in this form. Theta times a state supported on the WD subspace and the remaining part supported on the orthogonal. This is the structure of invariant states. Well, we can also introduce the notion of the tape balance. In this case, condition 11, this condition here is the condition for the tape balance. Sorry, it's not the tape balance, it's what we call local tape balance, because the k omega are constants that may depend only on the Bohr frequencies, but not necessarily has the form described here in this part. In the case where the k omegas have this form, this explicit form, then we have the tape balance, the usual tape balance. For weak coupling limit generators, there exists local tape balance invariant states that are not the tape balance. Okay, perhaps more interesting is that these weak coupling limit type generators can be characterized by an intrinsic property. The intrinsic property is described in terms of these subspaces, Dn, this written explicitly here. For instance, in the case when n equals 0, this 0 is the maximal abelian polynomial subalgebra of BOH generated by the one-dimensional projections associated with this basis, with these projections. Okay, the property that helps to characterize the weak coupling limit type generators is written here. The property P. The property is that for every integers n and for every frequency, the corresponding subspace Dn is invariant under the action of the L omega. This property almost characterizes the weak coupling generators because one can prove this lemma. If we have a generator satisfying property P, then we can show that the structure of the generator, the GKS-L structure, is given this form where the cross operators belongs to some of the subspaces previously described. More explicitly, each cross operator has these representations in terms of a multiplication operator and the shift operator, or this another expression. It's one of these two classes. Okay, this is a lemma. And the full characterization is given by this theorem. If a generator has a property P, then it has a GKS-L representation in terms of operators L sub L that are products of shifts and multiplications. And it is a weak coupling limit type generator if only if this additional technical assumptions holds. So this is a nice characterization of intrinsic characterization of coupling limit generators. In the case of low density limit, this is the general scheme to apply this stochastic limit method to obtain this class of generators. And this class of generators were started to be studied by Dumske in 1995. And later also has been studied intensively by Akardi, Lu, Akardi, Peche, Bolovic, and also in this class, also for this class, the generator is associated. This class are associated with a reference Hamiltonian, similar to the previous class. But in this case, all frequencies, all Born frequencies, positive, negative, and even the zero frequency plays an important role. The completely positive part of the generator is a sum, is an operator T that is a sum of operators T omega. Each operator T omega is associated with a positive, negative, or zero frequency. The T omega are may be in general unbounded, and they are described in terms of these kernels here in equation 15. That these kernels are depends on the spectral projections of the reference Hamiltonian, and the full information concerning this T operator is encoded in this family of operators T chi prime k that are assumed to be densely defined on a domain D, but not necessarily bounded. And this family encodes all the information, all the relevant information concerning the T operator, the completely positive part of the generator. Okay. So the structure of the generator is given this form. Here, T of X is denoted as sesquilinear form. And G is, as usual, given in this form. This is the usual structure, GTSL structure. The only difference is that we are considering here the unbounded case. This is the reason why appears here the completely positive part written as a sesquilinear form. The Hamiltonian part can be, well, we assume that that has this structure. This is rather complicated, but in some cases, relevant cases, we can assume that the effective Hamiltonian is indeed a function of the reference Hamiltonian. This is, for instance, the assumption we do in this work. This class of low density limit generators also have an interesting property of leaving invariant some subspaces and subalgebras. For instance, this they leave invariant the commutant of the reference Hamiltonian, and leave invariant also some non-other subspaces of the, of diagonal operators described here. This is the property. The generator leaves invariant the commutant of the reference Hamiltonian and also these subspaces. But we don't know if this property characterizes the class of low density limit generators, even in the case of bounded coefficients. The master equation associated with these generators has this structure, where the T star is also a sum of T omegas of pre-dual expressions, and they are in general densely defined operators acting on the trace class operators with domain Matcal D defined as the span of these projectors with B and U in a dense subspace of the initial Hilbert space. Okay, now let me pass to describe the generic the role of the generacies in this class of generators. First, let me recall that the generic condition, genericity condition, is a useful condition to distinguish generators with a simple enough structure that allows to compute, for instance, invariant states and to study the approach to equilibrium. These are references of the use of generic condition in the case of weak coupling limit type generators, and also in the case of the last one, in the case of the low density limit generators. Okay. From now on, we will assume that the spectrum of the reference Hamiltonian is non-degenerate. And in this case, the T omega operators have a very simple structure. In this case, they are essentially projectors, multiples of projectors, are rank 1 operators. Okay, so the role of the generacies. Well, let me introduce the definition of locally generic system Hamiltonian. We start with a Hamiltonian HS with a non-degenerate spectrum. We will call a frequency omega a G frequency, a generic frequency, if it is associated with only one pair of eigenvalues in the spectrum of HS. These are generic frequencies. And we will call the Hamiltonian HS locally generic if there exists at least one generic frequency. And we can, in this case, we can distinguish the subset that I denote here by S1 of those eigenvalues in the spectrum associated with generic frequencies, We call this the one generic sector of the spectrum. Some remarks. First of all, if the Hamiltonian HS is generic, all more frequencies are generic frequencies. Equivalently, the spectrum has only the one generic sector. All the spectrum is the generic sector is the whole spectrum. A generic frequency is necessarily non-zero. Moreover, if omega is a generic frequency, minus omega is also a generic frequency. If we have an element in the one generic sector of the spectrum, then this epsilon prime is also associated, is also belongs to the one generic sector. And the last observation is that the non-generic spectrum of a locally generic Hamiltonian can be split into the generic and the complement, the generic part and its complement, okay? So we will say that the Markov generator is locally generic if the Hamiltonian if the reference Hamiltonian is non-degenerate and locally generic. Okay, let me try to describe the intuitive idea behind this notion of generic, locally generic, and two generic notion. If we see to the spectrum of the reference Hamiltonian and to the spectrum of the corresponding Liouvillean, in the generic case, both spectra are non-degenerate.
Riccardo, non ti metti sugli aerei?
Sorry?
Che cosa avevi? E sto sentendo anche il conferenza, Riccardo.
Or it is a noise.
Ah.
Is too much noise? Can you hear me?
Yes, we hear you, but it was noise from other participants. Sorry.
Okay, I will continue. So in the generic case, both spectra are non-degenerate. In the locally generic, the spectrum of the reference Hamiltonian is non-degenerate, but the spectrum of the corresponding Liouvillean may be degenerate. Okay, this is the locally generic case. And in the two generic case, the spectrum of the Hamiltonian is non-degenerate, and the spectrum of the Liouvillean has only one two-degenerate frequency. I mean, there exists only one frequency of that satisfies the two generic conditions. The two generic condition is described here, but it's rather complicated, so I will not enter into the details. Let me say only that two generic frequencies are associated with two pairs of eigenvalues. This is the idea. Better to describe with some ideas. Describe the two generic block. Suppose that we have a two generic frequency. I mean, associated with two pairs of eigenvalues. Epsilon m, epsilon n, and epsilon m prime, epsilon n prime. Okay? This is the case when the two generic sector of the Hamiltonian is non-empty. Once we assume the existence of these two generic frequencies, immediately one see that minus omega and plus minus omega hat, where omega hat is defined in this form, are also two generic frequencies. Okay. Moreover, also assuming the existence of a two generic frequency, one obtains immediately that the one generic sector is non-empty. It's also non-empty. Indeed, there are at least two and at most four frequencies given in this form by these expressions that are generic. Moreover, these relations holds true. These relations here. And the generic, the zero frequency is always present, and this is not a two generic frequency, nor generic. Okay, except in the trivial case when the spectrum of the Hamiltonian has a cardinality 2. So this omega block is better described by this diagram, where we can see here the omega frequency, omega twice, the omega hat twice, and the generic frequencies omega g prime and omega g. Okay, this is a schematic representation of the omega block. Okay, so this block has and special distinguished is associated with a special part of the generator. The generator of the Markov generator associated with an omega block, when there exists only one omega block, is the sum of up to 4 generators associated with the 2 generic sectors, and up to 4 generators associated with the generic sector, and the zero frequency is always present. So for given a 2 generic frequency, it immediately distinguishes a block of the Markov generator that has up to 9 summands, 4 to generic, 4 generic, and the summand corresponding to zero frequency, assuming that there exists only 1 to generic frequency. So in this this is have a important consequence on the structure of invariant states. For instance, assume that we want to compute an invariant state, and we decompose the state in this part, the diagonal and the off diagonal part. So here is written the generator, general form, up to 9 generators, and the Hamiltonian that we are assuming to be the effective Hamiltonian that we are assuming to be a function of the reference Hamiltonian. The structure of the LA omegas is more simple. It's written in this form. And if we assume these Detail balance conditions that we call T-Detail balance conditions, we can simplify even more the generator so that we can write these conditions to give sufficient conditions to have invariant states, diagonal invariant states. These conditions written here that we call Detail balance conditions are sufficient for a diagonal invariant state to be invariant, and the form of this invariant state is written here. So we arrive to invariant state with this structure. And in general, well, there is an interpretation of these conditions, Detail balance conditions. We can give an interpretation in terms of this written in this form. These conditions means that the Kolmogorov's criterion for reversibility of the corresponding classical Markov chain holds true on the cycles, on these 3 cycles, M and N prime, M prime N prime, and M prime N N prime. Okay, this is a nice interpretation. And the general structure of a non necessarily diagonal invariant state is written here.
Sorry, you have 2 minutes. Sorry.
Okay, I'm going to the end. So this is the class of invariant states associated with an omega block with only 2 generic frequency. Okay, the similarity principle is a principle that in a more or less rigorous formulation says that if we have a full system of heat bath plus small system, the system drives. If the system is in a pre-Hamiltonian, the system has a pre-Hamiltonian HS, is driven by the environment to a certain invariant state, if only if this limit exists. And the environment drives the system with a pre-Hamiltonian HS to thermodynamical equilibrium if the initial state of the environment is an equilibrium state at inverse temperature beta, and there exists some initial states rho s such of the system, so that the final state is the Gibbs state at the inverse temperature beta. This is the formulation of the environment of the similarity principle. And to discuss the breaking of similarity principle, I consider the simplest case of a Hamiltonian with only 3 levels, the corresponding block diagram of the omega block of two generic frequencies. There's only two generic frequency and a generic frequency W omega. The another generic frequency omega G is 0. This is a very simple case. It's the simplest possible, in fact. The generator has only 5 summons. And this condition, this condition here, 39, is a sufficient, that is necessary and sufficient to have an invariant state, a unique invariant state, diagonal indeed, that is written here. And this invariant state is non-Gibbs, is not the Gibbs state, because the Gibbs state has this representation here. This is the Gibbs, the corresponding Gibbs, and this is the invariant state. And they don't coincide. So in this case, under these conditions, the Gibbs state is not even invariant. And okay, this is what we call the breaking of the similarity principle. Thank you very much for your attention.
Thank you. Any questions or comments, please? Well, maybe I have a question. Is it? I don't a bit understand. So, am I true that the correspondence between weak coupling limit type and low density limit type generators? So, is it true that usually low density limit type generators are more general than weak coupling limit types, or not?
No, I think they are different classes. So they are different. The weak coupling depends strongly on an interaction operator. Let me show you. There is an interaction operator associated with the weak coupling class. Sorry. And in the case of the low density, the main role, a principal role, is played by the T operator. That is something like a scattering operator. They are different classes, indeed. They are not.
And are there intersections of them? I mean,
I don't know. Maybe I guess that no intersection.
Maybe
I haven't examined with.
Maybe I can comment. Yes. Hello, Roberto. Glad to see you. So in a low density limit master equation is determined by T operator, transition operator, which if interaction between system and environment is strong, this T operator contains all series and perturbation theory. If you are, in addition to low density limit, assumes what interaction is weak, so like in consider for T operator Born approximation, then you will have here the situation exactly as in weak coupling limit. So in this case, you will have Gibbs states for Gibbs environment, etc. So if you, in addition to low density limit, assume what the interaction is weak, then you will have similar structure to the coupling limit case. But in low density limit, in general, interaction is strong in all terms of perturbation theory contribute to T operator. Therefore, it has similar behavior as weak coupling limit if interaction is addition weak, but otherwise it is more general and different.
So if we speak about structure of generators, it seems that weak coupling limit times should be some weak coupling limit of the low density type generators.
At least in the sense of talk of Roberto, Professor Quezada, if interaction is weak, Roberto, I think right, then you will not, if you consider Born approximation for T operator, so only interaction, because I remember I did these calculations, then you will not have, you will have identical situation to V coupling limit. If you consider instead of T only V, interaction Hamiltonian. And you need to consider higher order terms to get this difference in equilibrium states. So Alexander, answering to your question, I don't claim what generators are the same, but situation is similar in the sense of, situation the same in the sense of this detailed balance, etc. If you consider in addition to low density limit, the assumption of weak interaction.
Yeah.
Okay.
Thank you for your comments. Any other questions or comments?
Maybe I have a question.
Sure.
So I think that the notion of two genericity can be applied also to the weak coupling case, because the notion of two genericity is not a notion of weak interaction. Is a notion which is in some sense more intrinsic, because it's related to the spectrum of the system Hamiltonian. So I want to ask, did you try to see your diagram of two genericity in low density, how it simplifies in the weak coupling? Because in low density, the fundamental difference of weak coupling and low density is that, as you mentioned in your talk, is that in the weak coupling only strictly positive Bohr frequencies appear.
Yeah.
So the two genericity graph of the generator should be simplified. And there is the possibility that it reduces to the lambda or V configuration that have been studied very much in quantum optics. Did you check this point or not?
No, I haven't checked, but it seems interesting. Surely the diagram will reduce the low density limit diagram, the block associated with a generic frequency, a two generic frequency will simplify, possibly only to associated with 3 levels.
Yes, that is what happens in the lambda and V configuration in quantum optics. And since in quantum optics, they discovered a lot of interesting physical phenomena with this simple interaction graph of the generator, I guess that the generalization, the extension of this graph that comes in low density can be considered as the simplest physical situation that extends the lambda V configuration in quantum optics. So I think this is really a ground for an interesting collaboration with people who has a deeper understanding of the physical phenomenon together with mathematicians, because now this diagram comes out mathematically. But I think we should have a physical understanding, like the people of quantum optics deduce the physical understanding for the simpler V and lambda configuration.
Yes, yes, surely. Thank you for your comment, Vijay.
Okay, any other comments or questions? Well, if not, then thanks, Professor Roberto Quezada, and thanks all the speakers of this session.